video, we are going to be looking at the key features of a cubic. And because for some of you guys, it's the first time we've seen a cubic, we're going to build it from scratch. So cubic, because the degree is 3. And here I have just our basic starting x values. So -2, -1, 0, 1, and 2. If I do 2 cubed, that is going to give me 8. 1 cubed gives me 1. 0 cubed gives me 0. The negatives is where something kind of interesting happens. So -1 cubed really means -1 times -1 times -1. So far, most people have been really used to working with a quadratic. And whenever we raise a negative number to the second power, we always get a positive number because a negative times a negative is a positive. But here I'm doing it 3 times. And so we're going to start with the first one, and -1 times -1 is +1. That's what we're used to seeing. But now I also have to multiply it by -1 again. And 1 times -1 is actually -1. And so this is going to give me -1. I can do the same thing out to show you that it works for -2. -2 is going to give me -8. So immediately, just looking at this, I see some differences from the quadratic. I see that it was 2, 4 with the quadratic. This number got a lot larger, a lot quicker. I also noticed that I have numbers in the negative round. So if I plot this, I'm going to start with -2, -8, -1, 1, 0, 0, 1, 1, and 2, 8. As I connect these, I know from what I've seen from other graphs that this is going to be curvy. I'm not just going to draw a straight line through the center. I'm going to try and curve it as I go. And this is kind of our shape of what a cubic function looks like. Now, if I were to do this on the calculator, it would definitely look a little bit better, but it's about the best sketch we're going to be able to get for a cubic. We saw earlier that when we were talking about key features, we're going to talk about the domain and range. I want to know about intercepts, and I also want to know, is there any symmetry, as well as increasing and decreasing. And so cubics are kind of interesting as they don't have a perfect line of symmetry here. But I noticed that this shape and this shape are pretty much the same. They're just going in opposite directions. That is known as rotational symmetry. So this has what is known as rotational symmetry of 180 degrees. What that really means, if I were to cut my cubic function right here and I were to spin this, it would take me 180 degrees to go from here to lie perfectly on top of this one. I could have also gone the same direction. I could have grabbed this one and spun it this direction. So we have this rotational symmetry, which looks a little bit different than the type of symmetry we saw with the quadratic. Now, if we talk about the domain, once again, we said was, well, what numbers can you plug in? Well, we already talked about in our quadratic one that any type of number can be raised to an exponent. So my gut instinct is that this should be from -infinity to +infinity. It should be all real numbers. Also, I can see on my graph that this is just going to keep going on. There's no reason why this function should stop. And even though it's going to go down really quick, it is still going to be going to the left. I could plug in -10. I could plug in -1,000. I could plug in -1,000,000. Each of those are going to be able to go to the third power. So all the way to -infinity is going to work. And the same logic works in the right direction. So yes, my domain is all real numbers, -infinity to +infinity. When I move into the range, we're going to see something different from the quadratic. In the range of a quadratic, because it had this turnaround point, the range was restricted. It started at a very specific point and then went up, or it started at a very specific point and went down. But here, I don't have a turnaround point. My graph goes from the bottom all the way to the top. And so the range of a cubic function is also all real numbers. There's no restriction on our range. Similar to a quadratic, however, is the center point. 0 to any power always gives me 0. So any type of basic polynomial function, so x squared, x cubed, x to the fourth, x to the fifth, etc., is always going to have its x-intercept equal its y-intercept, which is at 0, 0. The last one we want to talk about here is intervals of increasing and decreasing. So a reminder from previous videos, we talked about increasing and decreasing means If I hop on my function, if I treat it like a roller coaster, is my roller coaster being pulled up a hill or are we going downhill? Well, here, when I hop on all the way to the left, this is the first place I see it, I can see that it's very steep and I'm being pulled uphill. It slows down for a little bit. It's less steep, but now it gets steeper again. But the entire time, even though the steepness changed, I was going uphill the entire time. So if I were to look at that, I am increasing, 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 increasing. So my intervals would be increasing is as soon as I hop on at negative infinity, remember that is x equals negative infinity. And then it ends, well, never, so at x equals infinity. The entire function is increasing. That would be my decreasing interval is non-existent, or NA for not applicable. And there you have it. These are the key features of the basic cubic function.